Assalamualaikum guys, this is part 4 of our chapter 6. Let's take a look at these two figures here. A real circuit on the left side, the schematic diagram on the right side. The source of EMF is maintaining a current in a closed circuit. It increases the potential energy of the circulating charges. Also, it can be thought as charge pump that forces electrons to move in opposite direction of the electrostatic field inside the source. Let's consider this schematic diagram. A positive charge is moving through a battery from A to B. As the charge passes from negative to the positive terminal of a battery, the potential of the charge increases by epsilon. As the charge moves through the resistor, this little r, potential decreased by IR, which is this current times the little r there. The terminal voltage delta V is equal to the epsilon if the current equals to 0 in an open circuit. The terminal voltage delta V must equal the delta V across the external resistance R, which is called load resistance. If you can see here, this is Ohm's law, delta V equals to IR. Substituted into the first one, we can get I equals to epsilon over load resistance R plus internal resistance R. Then the third one here, we just times everything with the current. And at the end of the day, we can have epsilon equals to IR plus IR with the small r. Okay, next, we have combination of resistors. When the two or more resistors are connected end to end, as in the figure on the left, we say they are in series. The resistors could be simple devices. For example, here, light bulbs, or it can be heating elements. When two resistors R1 and R2 are connected to a battery, the current is the same in the two resistors because any charge that flows through R1 must also flow through R2. The potential difference between A and B equals IR1, and the potential difference between B and C equals I times R2. The potential difference between A and C is given by the equation of this one. Delta V equals to IR1 plus IR2. It doesn't matter how many resistors we have in series. The sum of the potential differences across the resistors is equal to the total potential difference across the combination. Okay, now we have a schematic diagram of resistors in series. The equivalent resistance here can replace the two resistors of the original circuit, as shown here. Let us apply Ohm's law to equivalent resistor. Ohm's law, delta V equals to IR equivalent. This equation tells us that equivalent resistance of a series combination of resistors is the algebraic sum of the individual resistances and is always greater than any individual resistance. Note that if one of the resistors failed to operate, then the circuit would no longer be complete and the second resistor will also go out. Now let's consider two resistors connected in parallel, as in the figure here. In this case, the potential differences across the resistors are the same because each is connected directly across the battery terminal. The currents are generally not the same. When charges reach point A here, this is called a junction, the current splits into two parts, I1 and I2. I1 is flowing through R1, while I2 flowing through R2. If R1 is greater than R2, then I1 is less than I2. In general, more charge travels through the path with less resistance. Because charge is conserved, the current I that enters point A must equal the total current I1 plus I2 leaving that point. I equals to I1 plus I2. The potential drop must be the same for the two resistors and must also equal the potential drop across the battery. By applying Ohm's law to each resistor and to the equivalent resistor, and then cancel out delta V, we will get this relationship to calculate the equivalent resistor. This one applying Ohm's law for I1, applying Ohm's law for I2, and another one applying Ohm's law in equivalent resistance. Therefore, by cancelling delta V, we can have this I over RQ equals to I over R1 plus I over R2 and so on and so forth. From the expression there, we can see that the inverse of the equivalent resistance of two or more resistors connected in parallel is the sum of the inverse of the individual resistances and is always less than the smallest resistance in the group. Okay, this one is problem solving strategy for combination of resistors. We have 4 steps here. The first one, combine all resistors in series by summing up the individual resistances and draw a new simplified circuit diagram. Then use the equation for resistors in series. And remember, the current in each resistor is the same. Number 2, combining all resistors in parallel by summing up the reciprocal of the resistances and then taking the reciprocal of the result. Draw the new simplified circuit diagram. Use the equation for resistors in parallel. Remember, the potential difference here across each resistor is the same. And number 3, repeat those 2 steps. And last but not least, use Ohm's law or apply Ohm's law to determine the current in the equivalent resistor. And then we have to work backwards through the diagrams, applying the useful facts listed in step 1 until step 3.